there is nothing impossible for a dedicated person, but it will be more and more hard if they decide to continue after a break. So, how do you feel? Already tired and ready for the Christmas break?
Yeah.
Me too. So, what are we on? I know there are two things that freeze everyone. Remember what you did last time, and give examples of something. So, examples of oscillations. Who is oscillating?
Bonds.
Perfect. That's number one. What else is oscillating in our world?
Strings on musical instruments.
That's great. What else? Just, I plan to distribute the homework asking to answer it in writing. If we discuss it now, it will be easier. And it is not super hard. So any examples you saw in your everyday life, in other courses, in just your imagination related to science, if you focus your imagination on scientific things?
Waves?
Huh?
Waves?
Yes, yes, yes.
Those like inflatable like advertisement people that have like the big arms.
Sure, those are great examples. Have you seen on some outreach activity meetings chemical pendulum that changes color from transparent to dark blue? You missed this? You didn't do it in chemical club? I don't know if at lunch you get excited. Some people do, some do not. Like I do not get excited if things do not burn and explode, but some chemists really like when it like abruptly change the color, and it is very fine reaction when you need to do precise measurements. It's like steps of reactions, and one of the intermediate is color. It goes in cycles. But we are doing different kind of oscillations. Who has never seen cell phone? So what's the main principle of transmission of radio signal? Last time you already gave an example of electromagnetic waves, right? Because strength of electric field, magnetic field oscillate. That's a good example. They are oscillators in free space, fine oscillators of electromagnetic waves. What is this? Which circuit? Just read this. LC, yes. What is L? What is C?
L is an inductor and C.
So how does this circuit function?
So as it kind of oscillates between going from electric potential from the electric field potential.
I'm impressed. I'm in the surrounding of highly educated people. It is. So it is. Yeah, +2.
So the capacitor produces an electric field, and as current goes to the capacitor, it generates a potential in the electric field. And then eventually all the current and potential is generated in the electric field, and eventually goes back into the inductor, which generates electric magnetic field, and that's where all the potentialized.
That's great, really. And if you measure the amount of charge on the capacitor, it will oscillate the same. If you measure the strength of magnetic field inside this inductor, it will also oscillate like sine. They will be in opposite phases. But why this combination of capacitor and induction is used? some people may believe that it is the core technology of the whole human civilization. I know we're in chemistry, physical chemistry. It's not chemistry, but any ideas from your general education?
The transmitter?
Yes. Transmitter of what?
Radio wave.
Yes. So it is both transmitter and also receiver. So there is a junk circuit connected to it, but it is a heart of both transmitter and receiver. So you have this. If you are with your cell phone, you do have it. If you are just with little FM receiver, you have it. If you are putting the, well, not TV, but if you see spy movie of a person put this little buds that hear something and transmit signal secretly, they all have this transmitter, right? But it is an example of oscillations. There is another example of oscillations that are not related to chemistry, but it can be experienced by molecules or groups of molecules that do not have bonds between themselves. The solvents can be polar, right? Sometimes. For example, what is the most popular polar solvent?
Water.
Good. Something else? Ethanol, liquid alcohol. So they have like dipoles, and if you put a bigger molecule, bigger polar molecule, a molecule that changes its polarity upon during a reaction or due to hot excitation, then dipoles of a solvent will adjust to compensate electric field of the central molecule. But due to thermal motion, they will perform little rotations, not full rotations, but rotations forced and back in angle, like a compass. And there is a special word for this thing. Rotations. What are plasmons? Have you ever heard this word? Plasmons in gold nanoparticles, stained glass in cathedrals. No? So if, you know, there is a gold for cell, big chunks, or maybe not very big. There are like ions dissolved through electrochemistry, and there are nanoparticles when there are maybe 1,000 atoms. And they perform optical activity, they're able to absorb and emit light, but it is very different protocol, very different mechanism compared to semiconductors and regular molecules. Instead of one molecule going between orbitals, it is like many electrons inside the metal start to perform collective motion, to oscillate at certain frequency. So it's another example of oscillations, plasmonic oscillations in nanoparticles. So, when do we plan to do this stuff? Not coming Friday. No, in 2 Fridays. So, there will be meeting tonight in the lab to go over all the things. So the last time we finished somewhere here. So we did everything related to you and half of the questions selected by Caleb, and we should go maybe the whole this page and start another one. So that approximately it will be three pieces, and then on next Wednesday we will cover the rest, so that you will feel comfortable. There is a little homework, but it is much easier and much shorter. It is very quick math exercise that 15 minutes or 20. So it's not a main focus. Be sloppy. Focus more. Concentrate your effort on the MATLAB section and the code, because it will be used again and again later on. And in the navigation space between our methods, I was thinking of myself if I would be sitting on the other side of the barbed wire of a barrier. If I would be sitting in the classroom, I probably would draw this schematic diagram just on the first page and add on things as we go, because I don't know how about you, but I'm tired to copy paste it to redraw it every time. And if you plan to do it once again and then build up as a little house, you may leave a lot of space at the top. So it is a full page. Draw this section at the bottom and with a lot of space at the top, because we will be at the right. So right now, together with free space, one-dimensional blocks, three-dimensional boxes, and we are going to oscillators, harmonic oscillator, and we are making effort for solving time-independent equation with an additional tool. You are on the way to become certified experts in ladder operators. Right? So it is what we are doing here. It is a sale, a discount, a shortcut to get solution of time-independent equation with much less efforts. So we have formulated the time-independent equation as we usually do, as a combination of kinetic and potential energy, where potential comes from Taylor expansion of the interatomic forces near the equilibrium, and this R² term, elongation of contraction, makes challenge. We are trying to address. Here are the operators that I expected to help us to browse in the space of quantum states of harmonic oscillator to go up or down. There is an expectation that every evening before going to sleep, you open this page and try to memorize this equation. or at least you know where to take it. It will be used again and again. And it is not too hard. It is just superposition of position and momentum with two factors. And both factors have mass, frequency, and Planck constant just in different arrangement. So how did we benefited by now from these operators? What did they give us?
Ground state? Yes, thank you.
How does ground state look like?
It's like a Gaussian function.
Excellent, excellent. And what was the procedure to get the ground state? There was a philosophical component that we assumed that there is nothing below ground state. So if we try to lower ground state, to go lower than down below ground state, this operation is not permitted. We get zero. And by applying this annihilation, did I use this word? Going down means annihilation. So you cannot annihilate the vacuum. Vacuum will exist without referring to your existence or your chances to annihilate it. Right? So by annihilating vacuum, you get zero, and by solving the mathematical implementation of an equation that you are getting differential equation of the first order that has solution in form of Gaussian wave function, or we may note factor 2 here, and this combination of mass, frequency, and Planck constant, which are inverse with of this Gaussian wave function. We didn't found the normalization, but we know that it should be there. We should put some exact value for normalization. What are your expectations? How should it look like?
Like how to find it?
You all know how to find it. There is no challenge. It's trivial. By the way, today we are going to do just two things. We will take one integral and one derivative. Let's do it with glory. But sure, you will take square of the wave function, integrate, make sure that it is equal to 0, and solve for this unknown constant. But what are expectations? How the normalization factor should look like? What should it include? Should it be numerical factor of like 3/8, or it will be some combination of the frequency, mass, and Planck constant? Should it be the same for any oscillator, or it will depend on the what is oscillating?
I know what's oscillating.
Okay. And what should be in numerator? What should be in denominator?
Is it going to equal to Planck constant over MW?
Huh?
Is it going to equal to Planck constant over MW? And
It will be depending on the speed, right? So, but there will be the width will be in some power, either square root or maybe something more exotic. We'll check. It's 2 lines of derivation. Just guessing, and some of you may have already done it by non-important things. What else? Let's do it. There is no excuse for me to postpone this quizzing operation. So, must be equal 1. So we have n squared, right? 2 to the power minus and here the so what is in the numerator, what is in the denominator? And that is denominator.
Thanks.
It's reasonable. Yeah. But this was only phi, right? Phi naught. And we need phi naught squared. Right? How do you take square exponential power?
multiply the power by 2.
I do too. And then these two cancels. Right? What should we do next? I do not have energy, but it's a good idea. Next year, if, for the same class, just invite one by one and write a couple of symbols. Yes.
We change MW over 2 Planck's constant to 1 over sigma. with that's
So to introduce new variable.
yes.
Why?
Because MW over 2x constant is they're just constants, and you can just make it sigma that we can expression.
Yeah. So did you hear the suggestion? So there will be nice if we can replace this exponential into something more simple, that we know how to take the integral, to change variables. And if we agree, so if psi square is equal omega r square over h bar, then psi equals what? R multiplied by square root of omega over h bar. Agree? Was it your suggestion, or you were okay? So you just change variables. So instead of variable r, we will be using this Greek letter that we can pronounce as psi. And r everywhere can be replaced by psi times a bar over omega, and dr can be replaced by square root of a bar divided by d psi. I should be precise and not missing symbols, otherwise Alex will claim another point, catching my errors. So if we practice this substitution, then we will 1 equals e squared integral e minus psi squared square root of h bar divided by omega, which can be transferred to the both sides of integral d psi. So what is integral of, and the limit here from minus infinity plus infinity. If some of you is very picky and rigorous, there could be philosophical objections of if it is interatomic distance, how the change of this interatomic distance can be negative. We would mean that atoms smash into each other and go further. But it is just mathematical abstraction. In fact, the contributions from stuff far enough from equilibrium will not contribute to integration. But definite, we need to evaluate a definite integral of Gaussian of e to the power of minus psi squared. What is it? Yes, Alex is doing right. Sometimes in the past it was in the notes. We even spent the whole lecture by going from rectangular to polar coordinates, taking the square of this integral and then going to two-dimensional space, and then taking square root. So this is definite integral the area under Gaussian curve, so it should be some reasonable number, not very deep. Who is claiming the answer?
And
Can't find it.
isn't it 1?
No.
No.
It's either the square root of pi or 1 over the
Yes.
square root.
Square root of pi. Alex plus 1. Square root of pi, yes. Upper area of the screen is not cooperating. So what do we get? Yeah, it's the same thing as we did. So we have 1 equals n square root of h per m omega. Then the result of integration will be square root of pi. Can we solve it for n? N square equals square root of m omega divided by h pi. Yes, I should make a note and next year invite 1 by 1 to the board, because it's really affordable exercise. I just don't want to disturb you if you are relaxing. So what is the square root of square root? If square root is power 1/2, and taking square root is 1/2 of 1/2. Which?
4.
Right. And I can disclose that next couple of meetings I will try to practice the normalization for first and second excited states. So if it is ground, we put 0. Because normalization may be a little different for different states. So it was my cheat sheet and backup just in case no one will want to do actual work. So taking the integration, we get this normalization. So you did found ground state of harmonic oscillator. Now it is normalized. Why we need to normalize things? What is the benefit and necessity? What is the pleasure normalizing things? No pleasure, says Alex.
Does it become orthogonal?
Yes, orthogonal and orthonormal. And we all always need orthonormality to get rid of wave functions, right? When we convolute them. When do we get rid of wave functions?
Trying to find the expectations.
Yes, yes. Wave functions need to be normalized with the purpose, because these wave functions are not a tool to torture students. It is a tool to find expectation values. And if you do not normalize, you'll get huge error. So I was promising that we will do 2 glorious things. Take 1 integral and take 1 derivative. It's time for derivative. So I do not remember equation for raising and lowering operator. We need to cooperate. Maybe we need to memorize it together so that I keep it in memory. But if we do have, I will draw a picture, although we didn't provide all details for it yet. There will be some energies for ground first, second excited state, and we already know R, the ground state will be those. Now we need to find what it will be for the first excited state. And there is an expectation that if we just apply the raising operator, the diagram, to this we will get either phi1 or maybe phi1 divided by some constant. Okay? So we need three things. We need literal expression for ground state wave function. We need literal expression for raising operator. And we need a skill of taking derivatives. Good? Oh, okay. I did a little preparation. We are safe. We don't need to memorize anything, but just in case, please plan. It can be a really useful thing to memorize those. So by now we need only one skill to take derivatives. What do we see here? Larger amplitude. So it is the stuff that we just got. So minus r square m omega e bar and the factor 2 in the denominator, right? If it is wave function, there is factor 2. If it is wave function square, it disappears. There is a square root of square root m omega over pi e bar, which is power 1/4. And all the thing is so this is the same thing as we derived and studied before for raising operator. Remember, if it is raising a dagger or a plus, then between position and momentum there is minus. There is an imaginary unit in front of momentum. And remember, there were ugly constants of square roots of some h bar, mass, frequency. So if one takes the 1 over square root of mass and frequency and h bar out of brackets, it looks a little bit simpler. I should design a homework to check it. Next year. I had another idea for homework that you're safe. I'm just designing, maybe I will watch the recordings myself to make next year more pleasant. So I'm sharing just an idea. If you already have the ground state wave function, how do you know that we are not doing any heresy or alchemistry? There should be a way to prove it. And the way to prove it is to take your expression for ground state, this one, right? And plug it into Schrödinger time-independent Schrödinger equation. So it should keep the equality. If you plug it onto left and right side, do all operations, it should reproduce it, right? It will. But it is a great task to practice. For next year, you are busy. You have other things to do. And momentum is the only expression that I claim I can memorize. Minus I h bar derivative over position. So we plug in momentum here, and then open the bracket. There will be two terms. Once we just multiply ground state wave function by m omega position, and next we are taking derivative. Minus times minus 1 times so minus times minus will be plus, times I will be minus. So it will be minus h bar ddr. Square root minus h bar ddr square root e minus omega r square over 2 e bar. Chance for Alex and everyone else to catch the line.
Is I squared -1?
I squared
Yeah.
is negative,
Yes.
yes. But there will be,
Yes, let's see.
not this time. Thanks for the effort. So let's do glorious practice of derivative. The factor can be merged, transferred, sent outside of the bracket. So we need to take first order derivative. It's an ugly handwriting. I hate reading my own writing. So we need to take derivative of this exponential. Right? So ddr e minus 1 omega r squared to a bar. How do we take derivatives of exponentials? Derivative of exponential is exponential times derivative of everything that is in the power. So e minus omega r squared bar times d dr minus omega r squared h bar. How do you take derivative of r squared?
Multiply it by 2 and then leave on.
Huh?
You lower the power of r and multiply by 2.
Yep, correct. So we are getting e minus omega r squared. And this stuff is a constant. It just floats outside of the derivative. Minus m omega bar times derivative of r squared, which will be 2r. Right? Catch me if you can. It was just a title of code. What do you see? Do you see anything, any pleasant mathematical observations?
Oh, they're going to cancel.
What is going to cancel?
The stuff in the parentheses. Up from up top.
Well, I see that h bar will be cancelled. Which color primitives are?
Oh, it's minus
See,
1.
here we do have this h bar in here, right? In the denominator, and we have h bar there, so it will be cancelled, right? And then
It's negative.
the only
Negative.
result of taking derivative will be bringing here the factor of minus m omega r. Minus minus frequency. And then there was minus sign here and minus sign there, right? They will compensate each other. So it will be plus. What else? How does this factor compares to this factor? The same. And then the exponentials will be the same as well, right? So we will get the exponential stuff multiplied by twice m omega r, right? And there will be some constants. I'm not playing rigorous about constants because one would need to normalize it anyway. So the only important thing is that we have Gaussian style function multiplied by linear function. How would it look like? How can we plot it? So if you do have Gaussian, which is positive everywhere, then we do have linear, which is positive above zero and negative below zero. What are we getting after multiplying these two functions?
Equal but opposite, like comes on each side of the origin.
What if you be at the origin?
0.
0. What if you be at minus infinity?
Close to 0, but on the negative side.
Yeah. Good. What if you be on the plus infinity?
Same thing, but on the opposite side.
Okay. So it will be so just one little oscillation, right? Changing sign from negative to positive. Make sense? Right? So the it looks like good function from mathematical point of view because it decays to 0 at infinity, which tells that it is good to integrate, to take the definite integrals, derivatives, so there are no discontinuities, so one can play games. Good. Minus, plus. And right now we didn't play. We didn't play at all. We did hard and maybe not put on stuff. We didn't try to find the eigenenergies. Right now we are looking only for eigenfunctions. There is another part of solving time-independent general equation is to find eigenenergies, which we'll find later. And you already know from the particle in the box a standard way to graphically represent solution of time-independent general equation. You mix apples and oranges. You make a figure where y-axis is energy plus square root of probability. Right? So you plot orbitals which are offset by energy, and you also plot potential. So I'm skipping the values of these energies, although you may know that it is proportional to frequency times one constant. 1/2 h bar omega is 3/2 h bar omega, and then you to conversion. But you already know from your own effort, you are on the way to become masters of certified experts of weather operators. So you have the ground state which is Gaussian, and you have first state which is this Gaussian multiplied by linear, which comes to 0 in this shape. So if we would decide to do superposition and analysis of how the expectation value of position moves, you already can do it between ground and excited, similar as we did for particle in the box. We will postpone this pleasure for later. We better look for maybe at least one more excited states and energies, but you are on a right track of becoming experts of harmonic oscillator. End of the meeting. Thank you for attention and involvement into discussion. Special thanks for trying to catch errors and suggesting mathematical steps. And looking forward to see you 5 p.m. QBB 132. Dude, it's
The mic's right here, man. Spikes it.
Did it?